Electronic warfare in modern naval combat is not spectacular. It produces no fireball, no structural damage, no flooding report. It produces silence, a specific wrong kind of silence that experienced radar operators recognize before they can explain it. The silence of a system that is receiving information and returning nothing coherent from it. A ship that has been effectively jammed is a ship that has been rendered uncertain about its own environment. And uncertainty in combat is not merely an inconvenience. It is the mechanism by which an adversary converts technical sophistication into tactical advantage without firing a single round. The Iranian EW program had been a priority investment for the IRGC Aerospace Force for 11 years. The investment had been driven by a specific operational problem. The Aegis Combat System's SPY-1 phased array radar in its various configurations was the single most capable sensor the U.S. Navy brought to the Arabian Sea. And as long as that sensor was functioning, every Iranian weapons employment decision was being made against an opponent who could see farther, track more accurately, and respond faster than any of the weapons that could be deployed against it. The solution to that problem was not to match the sensor. The solution was to deny it, to produce an electronic environment in which the SPY-1's processing architecture generated so much noise, so many false contacts, so much internally inconsistent data that the system's operators could not distinguish real threat tracks from electronic artifacts, and the fire control solutions computed from those tracks were therefore unreliable. The system that the IRGC Aerospace Force had developed for this purpose was not a single jammer. It was a coordinated architecture, multiple high-power jamming transmitters operating in a frequency-agile, synchronized pattern designed to attack specific vulnerabilities in the SPY-1's clutter rejection algorithms. The mathematical filters that the system used to separate genuine radar returns from background noise. The architecture's effectiveness depended on the ability to transmit at sufficient power and with sufficient frequency coordination to saturate those filters without simply producing a white noise floor that the system could recognize and discard. It was, in the assessment of the signals intelligence analysts who had been tracking the program's development, a technically demanding achievement that had required a decade of development and testing to reach operational maturity. USS Gettysburg had been conducting independent operations in the northern Arabian Sea for 22 days. The ship was positioned in a sector that placed her between the primary threat axis from the Iranian coast and the logistics corridor serving the carrier strike group operating further south. Her SPY-1B had been running in full surveillance mode continuously for 22 days, and the watch team had been managing the Arabian Sea's electromagnetic environment, the commercial shipping traffic, the atmospheric ducting effects, the background noise of a busy contested maritime region. With the professional competence that 22 days of continuous operation produces in a crew that is already trained and that has been sharpened by repetition. At 1:33 a.m., the electromagnetic environment changed. Not all at once. Not with the dramatic clarity of a system going offline. The change was gradual, beginning at the edges of the SPY-1B's operational envelope and working inward. First, a slight increase in the false detection rate in the northern sectors, then a degradation of the track continuity on contacts at medium range. Then the progressive failure of the clutter rejection filters in the frequency bands that were being attacked. The system was not failing. It was being defeated from the outside, one processing layer at a time, by jamming that was precisely tuned to exploit the vulnerabilities that years of technical intelligence collection had identified. The EW supervisor identified the jamming architecture at 1:33:44 a.m. 44 seconds after the degradation began. His identification was not based on a library match alone. The jamming signal had been specifically designed to complicate library matching by incorporating frequency agility that changed its apparent signature at intervals shorter than the library's standard characterization window. The identification was based on the pattern of the SPY-1B's degradation. The specific sequence of processing layers that were failing, in the specific order that a jammer targeting those layers would produce, in the specific frequency progression that the intelligence assessment of the Iranian EW program had described as the expected attack profile. He was not reading the jammer. He was reading what the jammer was doing to his system. He called the TAO at 1:33:48 a.m. The TAO had 47 seconds before the SPY-1B's track picture degraded below the threshold at which fire control quality solutions could be generated. 47 seconds was enough time to do one thing well. He chose to activate the ECCM, the electronic countermeasures protocols that the SPY-1B's software included specifically for jamming environments, a suite of adaptive filtering and signal processing modes designed to recover radar performance in contested electromagnetic environments. The ECCM activation began at 1:33:51 a.m. The ECCM was not sufficient. The Iranian jamming architecture had been developed specifically against the known ECCM capabilities of the SPY-1B family. The adaptive filtering modes that the ECCM engaged were being attacked simultaneously with the primary tracking modes, and the processing architecture that the ECCM relied on was the same architecture that the jamming was degrading. The ECCM slowed the degradation. It did not stop it. By 1:34:36 a.m., 1 minute and 52 seconds after the jamming began, the SPY-1B's track picture had degraded to the point where the fire control system was generating warning flags on every active track. Track quality degraded, fire control solution unreliable. The Gettysburg was operationally blind, not completely without sensors. The hull-mounted sonar was unaffected. Acoustic systems were immune to electromagnetic jamming. The EW suite itself was still functioning. The irony of an electronic warfare engagement was that the system being used to characterize the jamming was operating precisely because it was a passive receiver rather than an active emitter. And passive receivers could not be jammed through the mechanism that was defeating the active radar. The infrared sensors on the ship's countermeasure systems were partially functional. The navigation radar, which operated on a different frequency band than the SPY-1B and had not been specifically targeted by the jamming architecture, retained a degraded but functional surface picture at reduced range. The navigation radar's range limitation was the critical constraint. Against a small, fast surface contact at low radar cross-section, the kind of contact that the C-701's launch platform represented, the navigation radar's effective detection range was perhaps 4 kilometers. 4 kilometers at the approach speed of an IRGCN fast boat was a terminal engagement timeline with no margin for a layered response. The fast boats had been waiting, 6 of them positioned in a holding pattern in the shallow water north of the Musandam Peninsula. Maintaining minimal speed and minimal electromagnetic emissions, their crews monitoring the Gettysburg's radar signature through passive sensors for the change that would indicate the jamming had taken effect. The change they were looking for was the cessation of the SPY-1B's scan rotation, the change in the electromagnetic emission pattern that indicated the system had been defeated or significantly degraded. At 1:34:40 a.m., 4 seconds after the fire control quality flags appeared, the fast boat formation commander confirmed the change and transmitted the activation signal. 6 fast boats accelerated from their holding positions at 1:34:44 a.m. At 40 knots, they would reach the Gettysburg's position in approximately 3 minutes and 20 seconds. Their weapons, the C-701 anti-ship missile, a short-range air-to-surface and sea-skimming weapon that had been adapted for launch from fast craft, were already in their launch configuration. Each boat carried 2 C-701 missiles, 12 missiles total from 6 boats on a combined approach that would place them at the Gettysburg's hull from 3 separate bearings. The navigation radar detected the first fast boat contacts at 1:35 and 12 seconds a.m. 28 seconds after the fast boats activated. The contacts were at 4.2 kilometers closing. The navigation radar was resolving them as 6 distinct contacts in a spread formation that the TAO's display translated into a threat picture that was unmistakably a coordinated attack approach. The TAO had the picture at 1:35:14 a.m. He had no fire control quality solutions from the primary radar system. He had 6 fast boat contacts at 4 kilometers on the navigation radar, which could provide bearing and approximate range, but not the velocity vector precision that a fire control solution required. He had the EW suite's characterization of the jamming transmitter locations, which had been built up over the preceding minute and 40 seconds and which provided bearing information on the jamming sources. He had the hull-mounted sonar, which was detecting the acoustic signatures of 6 high-speed surface vessels on the same bearings as the navigation radar contacts. He built his fire control solutions from what he had. The SM-2 fire control solution against a fast boat contact is not the same problem as the SM-2 fire control solution against a ballistic missile. The Standard missile was not designed for surface engagement. Its engagement envelope was optimized for airborne threats. But the SM-2 Block 3B carried by the Gettysburg had been used in surface mode in previous engagements, and the fire control system had a degraded mode targeting protocol that combined bearing data from multiple sensors: navigation radar, EW suite bearing, sonar bearing, into a composite targeting solution that was less accurate than a fire control quality track from the Spy-1B, but was better than nothing. And better than nothing was what the tactical situation was offering. The TAO committed the SM-2 battery in surface mode at 1:35:22 a.m. 8 seconds after the fast boat contacts appeared on the navigation radar. 6 missiles targeting the 6 fast boat contacts through the composite targeting protocol. Not precision engagements. Area denial engagements, putting warhead fragments in the space that the fast boats were occupying or about to occupy, hoping that the imprecision of the targeting solution was less consequential than the speed and volume of the response. The SM-2 launches lit the Arabian Sea at 1:35:22 a.m. in a rapid sequence that the Gettysburg's deck crew, those who had been on the weather deck when the jamming began and had been ordered below by the general quarters alarm, would have seen from any porthole as a series of white columns rising from the VLS cells and bending toward the northern horizon. 6 launches in 11 seconds. The ship shuddered with each one. 2 of the 6 SM-2 engagements produced kills. The composite targeting solution's imprecision had placed 4 of the weapons outside the lethal radius of their target contacts, but 2 had been close enough that the warhead detonations had destroyed their targets or disabled them. 4 fast boats remained. They were now at 2.8 kilometers. The C-701 launches began at 1:35:44 a.m., not all 4 boats launching simultaneously. A sequenced launch that placed missiles in the air in a pattern that the boat formation commander had calculated would arrive at the Gettysburg's hull in a compressed time window. Not a simultaneous impact, but an overlapping arrival that would force the point defense systems to engage multiple inbound tracks within a span of seconds that was shorter than the CIWS reorientation time between engagements. The 4 boats launched a combined 8 C-701 missiles over a 22-second window. 8 missiles on 8 tracks arriving at the hull engagement zone in a 4-second window. The phalanx systems were operating on their independent targeting architecture. The CIWS did not require the SPY-1B's fire control picture to engage close-in threats. Each CIWS tracked its own contacts with its own dedicated radar. And the jamming that had blinded the SPY-1B had not been targeted at the CIWS frequency band. The 2 phalanx systems began engaging the C-701 tracks as they entered their engagement envelopes. The geometry of 8 missiles arriving in 4 seconds from 3 bearings was the geometry that the Iranian planners had designed to exceed the CIWS coverage architecture. 2 phalanx systems, each capable of engaging one target at a time with a reorientation requirement between engagements, could address 4 targets in the time available if the engagement sequence was optimized and the geometry was cooperative. Against 8 targets arriving in 4 seconds from 3 bearings, the geometry was not cooperative. 6 C-701s were engaged. 5 were destroyed. 1 was disrupted, its guidance system damaged by a phalanx burst that did not achieve a kill, altering the missile's terminal approach trajectory in a way that moved its impact point from the hull's waterline to the hull's weather deck at a less than optimal penetration angle. 2 C-701s were not engaged before they reached the hull. The first struck the Gettysburg at frame 47, amidships on the starboard side, at the waterline, at 1:36 and 9 seconds a.m. The warhead detonated on contact. The penetration was at the waterline. The shaped charge's optimal impact geometry against hull plating. The detonation energy directed inward into the hull structure and the space immediately behind the plating. The space immediately behind the plating at frame 47 on the starboard side was the auxiliary machinery room, a space housing the hydraulic power units for the steering system, the emergency fire pump, and the high-pressure air system that served the ship's damage control equipment. The second C-701 struck frame 61, also on the starboard side, at 1:36:10 a.m., 1 second after the first. The warhead detonated against the hull plating at a height 2 meters above the waterline, a less than optimal geometry that produced a penetration smaller than the first warhead's impact, but still a penetration and still a detonation inside the hull, this time in the space above the auxiliary machinery room that housed the secondary damage control equipment locker and the sound-powered telephone junction box for the ship's aft communications ring. 2 simultaneous penetrations, 1 at the waterline, 1 above it, 1 in a space containing hydraulic systems, 1 in a space containing communications equipment. The Gettysburg had been hit twice in 1 second. The auxiliary machinery room flooding from the first penetration was the more urgent casualty. The warhead at frame 47 had opened the hull at the waterline, and the space was accepting seawater at a rate that the initial flooding report assessed at 200 liters per minute, a rate consistent with a waterline penetration of approximately 30 centimeters diameter. Not catastrophic, not manageable without action. An urgently demanding casualty that would become progressively more serious as the water level in the space rose and began affecting the hydraulic systems that provided steering power to the ship. The steering system's hydraulic power units were mounted at a height of 45 centimeters above the auxiliary machinery room's deck, a design choice that provided some protection against bilge flooding but not against the progressive flooding that a 200 liter per minute inflow would produce within 3 minutes and 40 seconds, at which point the water level would reach the hydraulic unit intakes and begin contaminating the hydraulic fluid with seawater. 3 minutes and 40 seconds. The flooding detail needed to be in the space and beginning the sealing sequence within that window. The flooding detail reached the auxiliary machinery room access at 1:36:44 a.m., 35 seconds after the first penetration. The space was ankle-deep in water and still flooding through the hull penetration at its rated rate. The petty officer leading the team assessed the breach geometry through the water. A roughly circular penetration approximately 28 centimeters in diameter at the waterline, with secondary fractures extending up to 12 centimeters in each direction along the weld seam that the shaped charge had exploited. Total affected area, approximately 50 centimeters by 30 centimeters, irregular. The wooden plug for the primary penetration took 41 seconds to seat. The secondary fractures complicated the geometry in the way that shaped charge penetrations always complicated the geometry, requiring the plug to be driven at an angle that addressed the primary channel while the packing material in the team's kit was used to address the secondary fractures simultaneously. The flooding rate dropped from 200 liters per minute to 63 when the plug was seated. The portable pump that the trailing team member had deployed to the space at 1:37:02 a.m. was rated at 250 liters per minute. It was already winning against the reduced inflow rate, and the water level in the space had stopped rising and begun to fall at 1:37:28 a.m. The backing plate was positioned at 1:38:11 a.m. and the hydraulic bladder sealed the remaining fracture geometry at 1:38:24 a.m. The flooding rate dropped to 8 liters per minute. Residual seeped through the bladder material. The hydraulic units were dry. Steering was intact. The sound-powered telephone junction box in the secondary damage control locker had been destroyed by the second C-701's fragmentation effects. The aft communications ring, the sound-powered telephone circuit that served the aft damage control stations, the engineering spaces, and the secondary con position, was offline. The DC teams working in the aft sections of the ship were now relying on runner communication and portable radio sets, both of which functioned, but both of which introduced latency into the information flow that the damage control coordinator in DC Central was managing. The latency was acceptable. It was not ideal. The electronics technicians who began the junction box repair at 1:39 a.m. completed the reconnection of the surviving circuit paths at 2:11 a.m., restoring the aft communications ring to partial functionality. The jamming had not stopped. The jamming transmitters on the Iranian coast were still operating, still degrading the SPY-1B's track picture, still preventing the fire control system from producing the quality of solutions that the ship's full weapons employment capability required. The 4 fast boats that had launched the C-701 salvo were withdrawing northward. They would not re-engage. Their weapons had been expended. But the surveillance architecture that had been watching the engagement and transmitting the Spy-1B's degradation status to the shore-based commanders was still in place. And as long as the jamming continued, the Gettysburg remained in a condition where a follow-on attack could be executed against a ship whose primary sensor was operating at severely reduced effectiveness. The EW team had been working the jamming architecture continuously since 1:33 a.m. At 1:38:44 a.m., 5 minutes and 4 seconds after the jamming began, the EW supervisor identified a pattern in the jamming signal's frequency agility cycle that he had not seen in the first minutes of the engagement. But that had become visible as his team accumulated more data on the signal's behavior. The cycle had a periodicity, a repetition interval in the frequency switching pattern that was short enough to have been masked by the random appearing behavior in the early analysis, but long enough to be identifiable once enough cycles had accumulated in the recording. The periodicity gave the ECCM something it had not had in the first minutes: a prediction. If the frequency switching cycle was consistent, the ECCM could anticipate the next frequency state of the jamming signal and pre-position the SPY-1B's clutter rejection filters to be optimized for the jamming-free window that occurred between each switching event. Not a complete counter, not a restoration of full performance. A crack in the jamming architecture that could be exploited to recover partial functionality in the windows between switching events. The EW supervisor briefed the TAO in 30 seconds and implemented the adapted ECCM protocol at 1:39:14 a.m. The SPY-1B's track quality flags began clearing at 1:39:44 a.m. 30 seconds after the adapted protocol was applied. Not all of them, not immediately. The partial recovery was consistent with the theory. In the windows between jamming frequency switches, the system was recovering sufficient tracking quality to generate fire control quality solutions on the most important contacts in its field of view. Between windows, the degradation returned. The system was cycling between degraded and partially functional in rhythm with the jamming signal's switching interval. The cycle interval was 4.7 seconds, partially functional for approximately 1.8 seconds of each cycle, degraded for the remaining 2.9 seconds. For a ship managing its own damage control and waiting for confirmation of whether follow-on threats were developing, 1.8 seconds of fire control quality picture out of every 4.7 seconds was significantly better than continuous blindness. The fleet commander had been informed at 1:36 a.m. The pre-planned contingency response was immediate. The EA-18G Growler on alert status aboard the carrier 60 miles south was launched at 1:38 a.m. to conduct offensive electronic attack against the Iranian EW transmitters on the coast. The Growler reached its attack orbit at 1:44 a.m. The jamming signal's coherence began degrading at 1:46 a.m. as two of the four transmitter sites were disrupted. By 1:49 a.m., the remaining two transmitters had been silenced. The SPY-1B's track quality flags cleared across all sectors at 1:49:33 a.m. The Gettysburg had been operating with a degraded or absent primary radar picture for 16 minutes and 23 seconds. In those 16 minutes and 23 seconds, it had been hit by two C-701 warheads, managed two flooding casualties, lost and partially restored its aft communications ring, and contributed an empirical characterization of the Iranian jamming architecture's frequency cycling behavior that the fleet's electronic warfare community would use to develop a specific optimized counter to this attack profile within 48 hours. At 2:15 a.m., with the flooding controlled, the partial communications ring restored, the hydraulic systems confirmed operational, and the SPY-1B back to full functionality, the Gettysburg transmitted her full damage assessment to the fleet commander. The report was 6 pages. The operational status summary was 1 sentence: the ship is fully capable and on station. Here are the numbers when the SPY-1B clears and the watch continues. 22 days of continuous patrol before the EW attack. 44 seconds from jamming onset to EW supervisor identification. 16 minutes 23 seconds of degraded or absent primary radar. 6 fast boats, 12 C-701 missiles in the coordinated attack package. 2 SM-2 kills in surface mode from composite targeting solutions. 8 C-701s in the terminal salvo, 2 reaching the hull. 2 hull penetrations in 1 second. 35 seconds from first penetration to flooding detail in the auxiliary machinery room. 3 minutes 40 seconds before flooding would have reached hydraulic unit intakes. 4 minutes 14 seconds to seat the plug, position the backing plate, and inflate the bladder. 1.8 seconds of fire control quality picture per 4.7 second jamming cycle. The crack in the architecture that the EW supervisor found after 5 minutes. 0 fatal outcomes among the crew. The Iranian EW architecture had represented a genuine technical achievement. The frequency agile jamming that had been developed over 11 years had defeated the SPY-1B's primary ECCM protocols for 16 minutes and produced the target conditions for a coordinated fast boat missile attack. The attack had placed 2 warheads inside the hull. The jamming had been operationally effective in exactly the way it had been designed to be. What the jamming had not factored in was an EW supervisor who had built his identification of the attack on how the degradation was happening rather than on what signal he was receiving, who had found the frequency cycling pattern at 4 minutes and 4 seconds, and whose adapted ECCM implementation had given the fire control system 1.8 seconds of quality picture per cycle before the Growler arrived to end the contest entirely. The crack was 1.8 seconds wide. The crew of the Gettysburg held it open long enough.